Hey everybody, welcome to another Bill Sky, the Assembly Guy. I'm excited about this one today because we're going to be finishing all of the number system lectures in this course, and this one is going to be on the hexadecimal number system. Now I hope you've watched the binary number system one. In fact, a lot of people have been looking at that video. So this one is going to be a lot like that one, except it's going to be a little bit shorter. We are going to have some demonstration at the end. We're going to be using Windows for that demonstration instead of Linux, because Windows has no problem with hexadecimal values in the Visual Studio debugger. So let's get right to it. So what is the hexadecimal number system? The hexadecimal computers do not use data. They actually don't store the data as hexadecimal numbers. Everything in the computer, again, on and off switches, they're all stored with binary values. That's just the way everything is stored. However, hexadecimal numbers are used so human beings, you and I, other programmers, can easily interpret the binary numbers. You could use decimal, but decimal is not really a power of 2. The decimal number system, 0 to 9, it's not really a power of 2, so you have some difficulties with that. But hexadecimal is, and there's also some other benefits to hexadecimal, which we'll see in a couple of seconds here. So hexadecimal numbers, base 16, can contain one or more of 15 different digits. It's 0 through 9 and A through F. Now the A's can be capitalized or the letters can be capitalized, it doesn't matter. Well, that's kind of weird, right? 0 through 9, A through F. We don't have any other numeric digits than 0 through 9. So the inventors of the hexadecimal, how it's represented to human beings, they added the A, B, C, D, E, and F. Now, what does that mean? Well, in this little chart down here at the bottom, we have the decimal value and then we have the associated hexadecimal value. So if you notice, decimal values 0 through 9 are exactly the same as the hexadecimal values 0 through 9. However, the number 10 decimal is actually the letter A, 11 is B, 12 is C, 13 is D, 14 is E, and 15 is F. So that's it. Now we're going to be doing a little bit of math here, a little bit of arithmetic. We're going to be getting into some more of this, but that's the base numbers. Those are the base digits and the decimal equivalents. So let's start off with an example here. So any value containing digits 0 through 9 and or letters A through F are a hexadecimal value. So in this case, FC43, because F is a valid hexadecimal digit, C is a valid one, 4 and 3 obviously are, that is a hexadecimal number. Now, how is that represented in binary? It's actually represented really easily. Every hexadecimal digit has 4 bits that define it, 4 bits. And remember what we said in the binary number system video, 4 bits is a nibble. So a nibble can contain any of the 16 hexadecimal digits from 0 through F, 0 through 9, and then A through F. So in the case of F, those binary bits are 1111. If you add all those up, it equals 15, which is what F equals, 15. C is 1100. So that number, I believe, is 12. So that is the number 12 in both binary and hexadecimal. The decimal value is 12. 4 is 0010, starting from the right to the left. 3 is 1100. So you put all those nibbles together, and that big long binary number you see there on the bottom right, that is the binary equivalent of the hexadecimal number FC43. No strange math, no strange arithmetic. It's very easy. Take each digit, separate it into 4 bits, and you've got the entire number. So as I showed you just a moment ago, a hexadecimal digit can be represented in 4 binary bits. Those 4 bits are called a nibble. Yes, a lot of students don't believe me when I tell them that, but that's actually the truth. And so 1 nibble can contain 1 hex digit. Also remember that a byte contains 2 nibbles, because a byte is 4 bits and a byte is 8 bits and a nibble is 4. So remember, a byte does contain 8 bits. So a byte which contains 2 nibbles 2 nibbles times 4 bits can contain 2 hexadecimal digits. So in this case, we've got byte 1 on the left and byte 2 on the right. We've got FC and 43. So this would be a word, a 4-byte word, if you watched our size of variables, integer variables, I believe, that video. So that previous FC43 can be stored in 2 bytes. And the bits, we take each nibble, so we take the 2 nibbles for F, that's on the left, that's in byte 1. The 2 nibbles for C, that's in byte 2, and you can see them there. Those are the 2 bytes that represent F and C. And then we separate those nibbles out even more, so we're just kind of digging down into the different sizes that represent each one. And again, you've got FC43 there. So we've got the values of binary, we've got the values of hex, and we've got the values of decimal. I created a nice little chart here where the hex values on top go from 0 through 9 and then A through F. And as you can see in the second row, one nibble, a nibble starts at all zeros. That's the hex value 0. It's also the decimal value 0. And it goes all the way to F, which is all the bits are filled up, and that's F. So that's an illustration of how a nibble, a single nibble, can contain the smallest hexadecimal digit as well as the largest. So that's one of the reasons why a hexadecimal is so commonly used, is because they are directly related to 4 bits. All right, so how do we go from decimal to hexadecimal? Well, it's kind of like binary, okay? Each position of a hexadecimal number has a decimal equivalent based on the power of 16. So instead of the power of 2 for binary, it's the power of 16 for hexadecimal. And the power of 16 begins at 0. So this is just like in our binary video. You can see over on the far right, position 1, which is position, actually binary, power of 16, 0. 16 to the 0 is 1. Then the next one is 16 to 1 is 16. 16 to 2 is 256. 16 to 3 is 4096. So a lot like binary, except you're dealing with multiples of 16 instead of just multiples, or powers of 16 instead of just powers of 2. So if the hexadecimal digit or number has a value greater than 0 in a certain position in the nibbles, you multiply that number by its power of 16 value. If the digit at that position is 0, you ignore it, or you can add the zeros together, but that's kind of strange. So here's an example. The number at the very bottom, 1C3B, how is that actually, what is the decimal value of that? Well, what you'll do is, you'll start on the right. I like to take the B, and the B, I believe, is 11. So we take 11 times 1, so that's 11. Then the next digit, 3, we take 3 times 16, because 16 to the 1 is 16. 3 times 16, and that is 48, I believe. And then we take the C, and the C is 12. The C is 13, I believe. 10, 11, 10, 11, 12. No, it's 12. 12 times 256. And we set that aside. Then we take 1 times 4096, and we multiply those together. And then we add them all together, and then we get our number. So here's an example. So let's take a look. 1C3B, 16 to the third times 1 plus 16 squared times 12 plus 16 to the 1 times 3 plus 16 to the 0 times 11. No, that should be 1. Oh, no, 11. That's true. So because B is 11, so we do those multiplications, we add them all together, and we get 7227. Now remember, what we did here was the 1, this 1 right here, that is the 1 right there. So we took 6, and that's because the 1 is located in the 4th bit, which is 16 to the 3rd. We can do the same thing with all of them. This C is 12. This 3 is that 3. And this B is that 11. So that's where the 1, 12, 3, and 11 came from. are from those positions. You want to convert from decimal to hexadecimal, it's just like binary conversion, except this time instead of dividing by 2, you divide by 16. Now you take that remainder and you convert that to a hexadecimal digit. So in other words, if the remainder is a 10, you convert it to an A. If the remainder is a 15, you convert it to an F. So here's an example. Let's convert 9822 to hexadecimal. So we take 9822, we divide it by 16, that's equal to 613. The remainder is 14, so that's an E. We take the 613, divide that by 16, we get 38 with a remainder of 5. We take the 38 divided by 16, we get a 2 with a remainder of 6. Then we take that 16, or we take that 2, I'm sorry. We take that 2, we divide that by 16, we get a 0 with a remainder of 2. We flip all those nibbles, and we get 265E as our hexadecimal value for decimal 9822. Let's try another one, 32467. We took 32467 divided by 16, we get 2029 with a remainder of 3. We take 2029, divide that by 16, we get a remainder of 13, which is a D. We take the 126, divide that by 16, that's equal to 7 with a remainder of 14, which is an E. And then we take 7 divided by 16, that gives us a 0 with a remainder of 7. We flip all those nibbles, and we get 7ED3, which is the hexadecimal value of decimal 32467. So I think what we need to do now is actually take a look at this inside of the debugger. And what we're going to do in our program is we're going to actually show how we can also do some arithmetic, add and subtract hexadecimal values. Hey, welcome back, and let's take a look at a demonstration of hexadecimal and do a little bit of arithmetic on it. So what we've got here is we've got our Windows 11 with Visual Studio open. I created a 64-bit application. It's the same one I used in the binary integer video. So let's go ahead and create a couple of variables. I'm going to create a simple byte variable. I'm going to define it as a byte, and I'm going to specify it as the number, I don't know, let's say FFFF. Now, if you do that, if you create a hexadecimal value that begins with a letter, you must begin it with the number 0. So there must be a digit before every hexadecimal literal or immediate value. And I'm also going to end it with an H. All right, so let's go ahead and save. And now, is that too big? Nope, it's a byte, and we've got actually 2 bytes there. Remember, each hexadecimal digit is a nibble, and there's 2 nibbles to a byte. So that's a little bit too big, so let's get rid of the 2 F's there. And let's go ahead and build this. And now let's debug it. Now we put a breakpoint over here on the line number 9, which is our no-op. That'll be perfect. So we'll go up to debug, start debugging, and we're going to go take a look at that byte variable. And what I did was I went up to debug, Windows, and select a memory window. I already had one selected for the previous demonstration, so that's open up already there. But if you don't have that memory tab, go ahead and select debug, Windows, memory, and then pick one of these. And here's that memory tab right there. Okay, so let's go and take a look at that variable. So I'm going to say ampersand byte variable. I'm going to right click, make sure that I'm 1 byte in hexadecimal, and you can see FF. Now if you right click on that and you select unsigned decimal, it's 255. So FF is equal to 255, unsigned. If I right click and say signed, it's a -1. If you took a look at our 2's complement video, you'll actually see how signed numbers, negative signed numbers are actually represented. All right? So there is our hexadecimal number FF. Now we're going to go ahead and press the stop button here, and let's go do something with that. So what I'm going to do is I'm going to move into the EAX or RAX register my byte variable. And actually the byte variable is That's a kind of big number. So what I'm going to do is I'm going to first move into RAX 0. So that's going to clear the entire RAX register. And then I'm going to move the byte variable. And I don't think I actually... Let's go ahead and move the byte variable there with the square brackets routed to dereference it. So we move that byte variable in there. I'm going to then add... And let's actually subtract 1. So I'm going to subtract from RAX1. Then I'm going to add to RAX1. So we're going to subtract 1 and then add 1. You'll see how the second F goes down to an E, and then when we add 1, it goes back to the F. So let's save and build that. Now, byte variable is small. It's only a byte, and it's not going to fit in there. So we got an error here. It needs to be the same size. So I'm going to do a little trick here. I'm just going to move ZX. We'll talk more about that when we get into more assembly language statements. So just for the demonstration, and there it goes. So let's go ahead and debug it. Okay, so let's get started. I'm going to click the step over to go over the no-op. Place the no-op again. Now I'm going to move 0 to RAX. Now I don't see the registers up here, so I'm going to say debug Windows registers, and there's my RAX. So I'm going to move 0 to RAX, do a step over, and we can see RAX changed to 0. I'm now going to move my byte value FF to RAX. So now RAX contains FF. I'm going to add 1 or subtract 1 from RAX. So that FF, 1 subtracted from F, should be an E, right? And that's exactly what it is. It's FE. I'm going to add 1 to that. And now it's FF again. Now, one last thing about math. I'm going to stop this. I'm going to add, I'm going to add to RAX another one more. And let's see what happens. So I'm going to build it. I'm going to debug it. And let's go ahead and run through this code pretty quickly. Okay, so our RAX is FF. Now watch what happens when I add 1 to FF. It turns to 100, huh? What do you mean it turns to 100? What is the math going on here? But why did that FF turn into 100? Well, let's go ahead and play around with that. What has actually happened there? So if you remember, if in the demonstration we had FF and we added 1. Now, remember we said add RAX1. Now, we'll talk more about the add, but what we're doing is we're adding 1 to whatever is in RAX. And what's in RAX is this big 64-bit number, just with all the zeros in front of it, FF at the end. So what happens when we add 1 to that? Well, just like if you add 9 plus 1, what do you get? Well, you get a 0 and you get a carry. And then you drop that carry down and you get 10. So if I add 1 to F, what do we get? Well, F is the last digit in the hexadecimal number system, so we get a 0 and we get a carry. If I add 1 to the second hexadecimal digit, F plus 1 is what? It goes to the next. There's nothing past F, so we have to drop down 0 just like we did 9 plus 1, and then we carry. And now we say 1 plus 0 is 100. So that's why FF plus 1 equals 100. Now, if the register RAX was much smaller, if the register could only carry 2 nibbles, then we would lose that 1, and the number would end up being 0, 0. But we'll talk more about that when we get into the registers video on assembly language. All right, so this isn't a classroom. You're not required to do this, but I got a couple of good programming challenges for you. And one of them is write a program which takes a hexadecimal number entered by the user and convert it to decimal. In the same program or a new program, write a program which takes a decimal number, integer, and convert it to hexadecimal. Do that in C, C++, Python, Java, whatever language you like, and use those divide by 16s. Use that range, that power of 16. Really great example, really great exercise. If you do that, you will understand the hexadecimal number system. And that's all she wrote. So I hope to see you at the next video.